In this video, I'm going to talk about another pattern that appears when you calculate the eigenvalues of a matrix. And this pattern is that the eigenvalues of a matrix are related to the determinant of a matrix and also to the trace of a matrix. Let's see how, because it's actually really elegant and really simple. So the determinant of a matrix A is simply equal to the multiplication of all the different eigenvalues. Okay, so you get the eigenvalues, you multiply them together, and the result is the determinant of the matrix. Okay, so let me write that down. And what do you have to do if two eigenvalues are degenerate, they are repeated? Well, you have to include them twice or three times, as many times as their algebraic multiplicity. Okay, so repeating any degenerate eigenvalues. Okay, next, how are the eigenvalues related to the trace of a matrix? Well, that's also really simple. The trace of a matrix A, which, if you remember, was simply adding the elements of the main diagonal, the trace of a matrix is equal to the sum of the n eigenvalues. So you add up all of the eigenvalues and you get the trace of the matrix. And again, you have to repeat any eigenvalue that is degenerate. So you simply have to add all of the roots of the characteristic polynomial. Okay, and finally, this has a very interesting consequence. If a matrix is triangular, so remember, a triangular matrix was one that had zeros all above or below the main diagonal. For example, an upper triangular matrix is a matrix that has some numbers that might or might not be zero, and then it has zeros all below the main diagonal. This is a triangular matrix. Yeah. You remember that the determinant of a triangular matrix was simply the product of the elements of the main diagonal, right? And the trace, so we know that the determinant of A is equal to A times B times C. And we know that the trace of A is equal to A plus B plus C. You just add the elements of the main diagonals. But if you compare these two equations with these two results, then it's obvious that the elements of the main diagonal for a triangular matrix are equal to the eigenvalues. So you know that lambda 1 equals A, lambda 2 equals B, and lambda 3 equals C. So the eigenvalues are simply the elements of the main diagonal. This means that if in a problem I give you a triangular matrix or maybe a diagonal matrix that has zeros both up and down, then this also applies. Then I ask you to calculate eigenvalues. Don't do the procedure. Just say the eigenvalues are equal to the elements in the main diagonal because the matrix is triangular. Okay? And you save a lot of time.